Hello everyone. Today I wish to discuss the question, how well can multiple parameters be estimated simultaneously? This talk is based on a paper we have recently published titled Efficient Computation of the Nagioka-Hayashi Bound for Multi-Parameter Estimation with Separable Measurements. This work and my talk focuses on attainable bounds in quantum metrology and in particular the role that separable measurements have to play. Hopefully, by the end of this talk, I will have convinced some of you of the importance of separable measurements and by extension, our results. I'll begin with an outline of our results. Our main result is that we present a new bound for parameter estimation, which we call the Nagioka-Hayashi bound. This bound is useful for two main reasons. It is valid for separable measurements on a finite number of copies of the probe state, and this is in contrast to the more commonly used Holevo bound, which in general can only be reached with a complex collective measurement on infinitely many copies of the probe state. For this reason, the Nagioka-Hayashi bound is, in general, tighter than the Holevo bound. We named the bound in this way after two important papers. The original separable measurement bound was introduced by Nagioka for the estimation of two parameters. For the case of estimating physical observables, Hayashi extended the original Nagioka bound to more than two parameters. And our contribution is to write down the generalized Nagioka bound for parameter estimation based on Hayashi's method. We have further shown that this bound can be computed efficiently, making it easily accessible. And finally, we've illustrated the importance of this bound with two physically motivated examples. So I'll first describe a measurement in quantum mechanics. We have a quantum state S, which we will measure to learn something about our system. Say we have n parameters of interest, denoted here by the different thetas. This is just a 1 by n vector, which we wish to learn as accurately as possible. And these theta describe the quantum state and may represent physical quantities that we wish to learn about. These quantities are encoded on the density matrix of the system, and this generally happens in one of two ways. Either we wish to learn something about the quantum state itself, or the quantum state passes through some channel, and the parameters of the channel are encoded onto the density matrix. In order to learn about these parameters, we then measure the quantum state. And the most general measurement in quantum mechanics is a positive operator valued measure, or POVM, denoted here by pi m. There are some conditions these POVMs need to satisfy in order to be a physically meaningful measurement. And based on the different measurement outcomes that are obtained, an estimate of theta is produced through some estimator function. And if we repeat this enough times, the estimated values should converge to the true values. And we quantify how well a particular measurement and estimator performs through the mean squared error matrix, denoted here as V. And we don't need to worry about this too much. It basically just tells us how good a measurement is. And it's natural then to ask, just how good can a measurement be? Although quantum resources can benefit measurement precision, in some respects, quantum mechanics can actually be detrimental to measurement precision. For example, the uncertainty principle implies that we cannot measure any number of quantities with an arbitrary precision. And the ultimate limit on how well a set of parameters can be measured was introduced by Holevo and has since become known as the Holevo bound. A similar bound was introduced by Nagioka and is referred to as the Nagioka bound. In the form shown here, the Nagioka bound is applicable only to estimating two parameters. And we now add a new bound to this list, the Nagioka-Hayashi bound, which generalizes the Nagioka bound to estimating more than two parameters. As this bound can be computed efficiently, it should be easily accessible. All of these bounds involve an optimization over Hermitian matrices. We'll now look at the difference between these bounds. So in his paper, Nagioka introduced another bound, which he called the most informative bound, denoted here as CMI. And this was defined as the minimum variance which can be achieved by any POVM and unbiased estimator. In general, this bound is a tighter bound than the Nagioka bound, which is in turn tighter than the Holevo bound. The Nagaoka bound and Nagaoka-Hayashi bound coincide for estimating two parameters and apply when we restrict ourselves to separable measurements. In contrast, in order to reach the Holevo bound, we require, in general, a collective measurement. Now, in some specific cases, this isn't true, and the measurement strategy required to reach the Holevo bound is known, but in general, a much more complex and experimentally challenging measurement is required to reach the Holevo bound. So a separable measurement means that we can measure our probe states individually. So we prepare and measure our probe states one by one. Whereas with a collective measurement, we are required to measure all of our probe states simultaneously. And obviously, this is considerably more experimentally challenging than a separable measurement. And this is the main motivation for our work. The Nagaoka-Hayashi bound, being a bound on separable measurement precisions, represents an experimentally feasible bound. This brings us to our main results. Without going into too much detail, we write the variance from the optimal POVM and estimator as V star. This is the best possible measurement precision when restricted to separable measurements. We write V star in terms of S theta and L star theta. S theta is an extension of the quantum density matrix of the probe state in an extended classical quantum Hilbert space. And L theta is a set of operators on the same extended Hilbert space made up of the tensor product of the classical matrix of error elements with the different POVMs. For convenience, I've shown L theta here for the estimation of three parameters, and L star theta is the optimal L theta, which minimizes the total variance. With this notation, we can write the Nagaoka-Hayashi bound as shown as a minimization over the matrices L and X. This is a new bound for multi-parameter estimation with separable measurements. We have further shown that this computation can be recast as a semi-definite program, meaning the minimization problem involved in this bound can be computed in an efficient manner. Prior to this, when computing separable measurement precisions, the most common approach was to explicitly try and find the optimal measurement strategy, i.e. to find the best POVMs and estimator. However, as the dimensions of the system in question grows, this becomes computationally expensive very quickly, and our program offers a method to circumvent this. I'll now illustrate our results with two physically motivated examples. Our first example is the problem of trying to estimate three rotations about the X, Y, and Z axes of the Bloch sphere using a 2-qubit probe. Our input state is the maximally entangled 2-qubit state, and 1 qubit in the probe experiences the different rotations and is then subject to the phase damping channel. The effect of the phase damping channel is to shrink the Bloch vector along the X and Y axes, and the second qubit experiences only the identity channel. And we want to know how well can we estimate these rotation angles. In this figure, we show the Holevo and Nagaoka-Hayashi bounds for simultaneously estimating these rotations. The Holevo bounds are shown as solid lines, and the Nagaoka-Hayashi bounds are shown as dashed lines. For estimating a single parameter, the two bounds coincide. However, for estimating 2 or 3 parameters, the two bounds are different, and the shaded region corresponds to the gap between separable measurements and collective measurements. For the 3-parameter case, we see that although separable measurements are inferior to collective measurements, the gap between the two is quite small. And this suggests that it may not be worth searching for the optimal collective measurement strategy, as the benefit from the potentially complex collective measurement required is not that large. And our bound also allows finite size effects to be studied in quantum metrology. Here, we are evaluating the difference between collective and separable measurements for estimating 2 or 3 parameters. We evaluate this difference when measuring a single copy of the probe state, shown as the blue lines, when measuring 2 copies of the probe state simultaneously, shown in red, and when measuring 3 copies of the probe state simultaneously, shown in black. So our bound offers a method to investigate the asymptotic attainability of the Holevo bound. And our second example concerns the simultaneous estimation of phase and loss in an interferometer. we consider the most general photonic input states of the form shown, which have a maximum of n photons. And for all n up to and including 14, we found that the Holevo and Nagioka-Hayashi bounds coincide. And we were actually able to show that there always exists a POVM which reaches the Holevo bound. And this implies that for this particular example, collective measurements offer no advantage. So rather than searching for some complex collective measurement to saturate the Holevo bound, if we know the two bounds coincide, we can focus instead on searching for a separable measurement which will reach the Holevo bound. I'll leave you with two very interesting possible avenues for future work. An obvious question is whether or not the Nagioka-Hayashi bound is always attainable, i.e., can we always find a separable measurement scheme which reaches the Nagioka-Hayashi bound? In the two examples that we have considered, we found this to be true, but it's not necessarily true from the way the bound is constructed. And the second question concerns the attainability of the Holevo bound. So in general, we know that a collective measurement on infinitely many copies of the probe state is required to reach the Holevo bound, and the Nagioka-Hayashi bound allows us to investigate this. This is something we've been working on and will hopefully share soon. And finally, I'd like to finish by thanking everyone involved. I'd like to thank Jun Suzuki, Pinkoy Lam, and Saeed Assad. And my apologies for not being able to present in person, but if you have any queries, my email address is shown, and please feel free to get in touch. Thank you.